Welcome to this explainer. I'm absolutely thrilled to guide you through today's topic. We're going to explore the microscopic structures that literally shape the macro world around us. We are, of course, talking about polymeric materials. Now, giving you a solid intro about polymeric materials is really important because while you might hear the word polymer and instantly just think of cheap plastic water bottles, that is barely scratching the surface. It's a truly fascinating world of advanced material chemistry, and I can't wait to get into it. So let's dive right in.
Right off the bat, what do your DNA, your smartphone screen, and a non-stick frying pan actually have in common? I mean, it sounds like the setup to a really strange joke, right? But the answer is essentially the key to modern engineering and, well, biology too. They are all fundamentally reliant on polymers. From the literal genetic code that builds your body to the high-tech device in your pocket, polymers are everywhere.
Here's our roadmap for the explainer today. 1. An intro to polymers. 2. Everyday plastics. 3. Thermoplastics versus thermosets. 4. Conducting polymers. And finally, 5. Biodegradable polymers.
Okay, let's kick things off with Section 1, Introduction to Polymeric Materials.
So, what exactly is a polymer? Doing a quick refresher on these materials is absolutely crucial because understanding them is the literal foundation of modern engineering. The word itself actually gives us the biggest clue. In Greek, poly means many, and mer means units. So a polymer is just a massive molecule, a macromolecule, made by linking together a huge number of smaller, repeating molecules called monomers. Think of a single monomer as one single Lego brick, or maybe a single train car. On its own, it's just one unit. But when you snap hundreds or thousands of them together end to end, you get a massive, structurally sound chain. That chain is our polymer. And the number of repeating units in that chain? Chemists call that the degree of polymerization.
Let's see how this building process works in reality with something you likely use every single day, PVC, or polyvinyl chloride. You start with ethene and hydrogen chloride, and a catalyst helps them form vinyl chloride. That vinyl chloride is our monomer, our single Lego brick. Then, through heating and a chemical initiator like benzyl peroxide, those individual vinyl chloride molecules literally snap together. They break their double bonds to form a long, continuous chain. In chemical notation, you'll often see a little N outside a bracket, and that just represents the hundreds or thousands of those repeating units. That chemical chain is exactly the tough, durable material making up the water pipes in your home.
Moving right along to Section 2, plastics, the everyday heroes.
Plastics have replaced traditional metals and ceramics in countless applications, and it's mainly because of plasticity, meaning they can be permanently deformed and molded into shapes using heat and pressure. Plus, they cost almost nothing to fabricate. They have incredibly low densities, meaning they're super light, which makes transporting them a breeze. Yet, despite being lightweight, they still possess incredible mechanical strength. Add to that the fact that they don't rust like metal, they're highly resistant to corrosion and moisture, and they serve as fantastic thermal and electrical insulators. It's a pretty unbeatable combo.
For a perfect example of these properties in action, we can talk about PMMA, polymethyl methacrylate. You probably just know it as acrylic or plexiglass. It has these amazing glass-like qualities, incredible clarity and light transmission, but it's entirely a polymer. Because it's shatterproof, scratch-resistant, and moldable into virtually any shape, it's the absolute hero of LED TV screens, smartphone displays, car windows, and even the incubators used in hospitals. We get the beauty and clarity of glass without the fragility, all thanks to its polymer chain structure.
That brings us to Section 3, Thermoplastics versus Thermosets.
Now, not all plastics act the same when things get hot. The crucial difference really comes down to how the polymer chains are arranged. First, we have thermoplastics. Think of these a bit like wax. They consist of long, linear chains held together by relatively weak forces. When you heat them, they soften. You can mold them, cool them, and if you mess up, no big deal. You can just heat them up and reshape them all over again. On the flip side, we have thermoset resins. These are much more like baking a cake. During their formation, they create a highly cross-linked, three-dimensional network of strong covalent bonds. Once they are heated and set, they are permanently locked in. They're hard, they're strong, but you absolutely cannot melt them down and reshape them. If you try to heat them too much, they won't melt, they'll just burn and decompose.
Take a famously tough thermoplastic you probably have sitting in your kitchen right now, Teflon. If you look at its structure, it has these highly electronegative fluorine atoms surrounding the carbon backbone, like a microscopic suit of armor. This incredibly strong attractive force gives Teflon immense toughness and extreme chemical resistance to pretty much everything. That is exactly why nothing sticks to your Teflon frying pan and why engineers rely on it for high-temperature seals and heavy-duty electrical insulation.
All right, let's jump to Section 4, Electric Plastics, Conducting Polymers. So, since we were kids, we were taught a simple rule. Metals conduct electricity, and plastics insulate against it. I mean, that's why copper wires are wrapped in plastic, right? But under very specific conditions, some polymers, known as intrinsic conducting polymers, can actually conduct electricity just like metals. Crazy, right? How does that work? Well, it's all about something called the intensive conjugation of pi bonds. Simply put, the chemical structure of these specific polymer chains creates a sort of superhighway of delocalized electrons. These electrons aren't stuck orbiting just one atom. They are free to move along the chain. And moving electrons is exactly what an electric current is.
Now, to turn these polymers into highly efficient conductors, scientists use a process called doping. It's actually very similar to how we make silicon semiconductors. It breaks down into a simple three-step concept. First, you take that polymer backbone that has those conjugated pi bonds. Second, you either oxidize it by removing an electron, which we call p-doping, or you reduce it by adding an electron, that's n-doping. Step 3 is where the magic happens. This process creates highly mobile charge carriers, positive holes or negative electrons that dramatically increase the material's ability to conduct an electric field.
Let's think about n-doping in action on a polymer called polyacetylene. By adding a reducing agent, say sodium naphthalide, to the neutral polymer chain, we force an extra electron onto the chain itself. What you really need to take away from this is that these negatively charged carriers are now super mobile. When you place this plastic in an electric field, those charges easily flow, acting exactly like a flexible plastic wire to conduct electricity. The real-world applications of these conducting polymers are honestly revolutionary. Because they're lightweight and flexible, unlike rigid, heavy metals, they're being used to make advanced rechargeable batteries. They're also highly sensitive, which makes them perfect for analytical sensors that test pH levels, oxygen, or even blood glucose. In the medical field, their electrical properties are being leveraged for controlled drug release and even targeted cancer chemotherapy. And of course, they are paving the way for the next generation of flexible solar panels and LED displays. It's truly space-age stuff happening right now. And that brings us to our final stop, Section 5, the future, biodegradable polymers. As amazing as synthetic plastics are, we're all very aware they have a massive environmental downside. They do not break down easily. But the thing is, nature has been the master polymer engineer all along. Long before humans synthesized PVC or Teflon, nature was building perfectly biodegradable polymers. Polysaccharides like starch and cellulose in plants, proteins like silk, wool, and the gelatin in our own bodies. These are all natural polymers. They do their structural job, and when they are no longer needed, naturally occurring microorganisms like bacteria and fungi break them down into completely harmless water, CO2, and biomass.
So taking inspiration directly from nature, material scientists are synthesizing our own biodegradable polymers. For example, consider the chemical condensation of lactic acid into PLA or polylactic acid. Lactic acid is just an organic acid found naturally in biological processes. By linking these monomers together, we create PLA. It is a synthetic plastic, yes, but because it's derived from biological sources, it retains that crucial ability to be safely degraded by microorganisms when its job is finally done.
And the engineering applications for PLA are truly science fiction turned reality. Not only is it used for environmentally friendly packaging to help solve our global waste crisis, but it's also a shape memory polymer. That means you can deform it, but when heated to a specific temperature, it remembers and snaps right back to its original shape. Because of this, and the fact that it safely dissolves in the human body, it is heavily used in the biomedical field. We're talking about self-healing medical devices, cardiovascular stents that expand in an artery and then safely dissolve away over time, and surgical sutures that just disappear once your wound is completely healed. So we started with a simple Lego brick concept of a molecule, and we've ended up with plastics that conduct electricity, memorize their shapes, and seamlessly dissolve into the earth or our bodies. It leaves us with a thrilling question to end our explainer on today. As we continue to engineer polymers that heal themselves and biodegrade, what will the plastics of tomorrow actually look like? The building blocks might be invisible, but the possibilities are truly massive. Thank you so much for joining me, and keep exploring.